Welcome to class. In today's class, we are going to be looking at oxidation numbers. And be that as it may, what are oxidation numbers? In redox reactions, it is possible to know the electron loss and electron gain by use of oxidation numbers. Redox reactions can be best recognized by the use of oxidation numbers. That's what I mean, because when we talk about redox, we're talking about reduction and oxidation. So what are oxidation numbers? The oxidation number of an element in a particular molecule or ion is the electrical charge it appears to have by a set of arbitrary rules. So the electrical charge that an element appears to have in a particular molecule or in a particular ion, that charge as determined by a set of rules is what we call oxidation number. These rules guides to some extent the IUPAC nomenclature of a particular compound. And by using these rules, it is also possible to calculate the oxidation number of a particular element in a compound, provided that the other elements are known. Using these rules, it's also possible to calculate the oxidation number of a particular element in an ion, provided that the other elements are known. Let's look at the rules for assigning oxidation numbers. Rule number 1. In the first rule, it says that the oxidation number of an element in its free state or at ground state is equals to 0. The oxidation number of an element or an atom in its free state or at ground state is equals to 0. If an element is in its free state, it means it's at ground state. You can also say that that element is in a state which is uncombined with any other element. Example. In the first rule, so that rule, if we are representing the oxidation number of an element in its free state, we usually write a 0 as a superscript. A 0 as a superscript, alright, in the top right corner. For example, this is how to represent the oxidation number of sodium in its ground state. The oxidation number of, let me use an element like magnesium in its ground state. The oxidation number of aluminum in its ground state. The oxidation number of, think of other elements, nitrogen in its ground state, oxidation number of chlorine in its ground state. The reason why I'm writing Cl2 is because chlorine is a diatomic gas. It does not exist as a single atom in nature. Alright. We can also look at oxygen. It's 0. Alright. An oxidation number of an element like phosphorus is tetraatomic, 4 atoms is 0. So in the first rule, that's rule number 1, we have that. Moving forward from there, we can see, now look at this chemical equation. A chemical equation between sodium and oxygen. I didn't write O. Oxygen is a diatomic gas. Alright, I'm going to have Na2O. Alright, that's sodium oxide. this is solid, this is gas, and this is solid. Alright? If I want to balance a chemical equation, is balanced now. The right hand side is balanced. Alright, the left hand side, I'm going to put 4 here. So a balanced chemical equation right here to illustrate the combustion of sodium in the presence of oxygen to give sodium oxide. The oxidation number of sodium here is 0. But you will notice that I did not represent 0 up here. So this sodium is at ground state. It's not reacting, it's not combining with any other element. Most times, the 0 is often omitted. This 0 is oftentimes omitted. So because I didn't put 0 here, this does not cancel the fact that this atom is still at ground state. The 0 is often omitted in practical chemical equations. The oxidation number of oxygen here is also 0. Yes, it's 0. So that's the first rule for every atom at ground state. Let's look at rule number 2. Rule number 2 says that for a simple ion, when I'm talking about a simple ion, I'm talking about a monoatomic ion, an ion that consists of only one element. So for a simple ion or a monoatomic ion, the oxidation number of a simple ion is equals to the sign and the charge of that ion. I take it again. The oxidation number of a simple ion or the oxidation number of a monoatomic ion is the same as the size and the sign of that ion. Examples of monoatomic ions or simple ions. So in rule number 2, so we have Na plus, alright, we have Al3 plus, alright, we have other ions, Mg2 plus, we also have Cl minus, we also have S2 minus, and we also have the others. But let me just add one more to this. One more to this. Alright, I have F minus, that's fluorine ion. In this rule, these are ions. Ions carries a charge, which could be positive or negative. So this rule says that the oxidation numbers of this ion, alright, ions are, so for sodium, the oxidation number is +1. For aluminum, oxidation number is +3. For magnesium, because the charge is 2 plus, oxidation number is +2. For chlorine, because the oxidation number is minus, this is something as 1 minus, oxidation number is -1. And for this, oxidation number is 2 minus, oxidation number is -2. And for fluorine ion, oxidation number is -1. So this is the second rule for assigning oxidation numbers. If you look at this, you would notice that the oxidation number for an ion like this, the oxidation number, the sign is usually written before the numerical value. The plus or minus sign is written before the numerical value, before the numerical value. But while we are writing the charge as part of the ion, you see that the numerical value comes first before the charge. Numerical value comes first before the charge. This is the same thing as 1 plus. But writing the oxidation number, you don't write the oxidation number as 3 plus, but you write it as plus 3. The plus or the minus sign always come before the oxidation number. So this is the second rule. Rule number 3. Rule number 3 says that the oxidation number of a polyatomic ion, that is an ion consisting of more than one element. That the oxidation number of a polyatomic ion is the algebraic sum of the elements, the algebraic sum of the oxidation numbers of the elements present in that ion. I take it again. The oxidation number of a polyatomic ion, that is ion consisting of more than one element, is the algebraic sum of all the oxidation numbers of the elements present in that ion. Take for instance, alright, OH minus. This ion is called hydroxide ion. So take for instance this ion. This rule says that the oxidation number of this ion, the sign you are seeing here, this minus you are seeing here, that's minus 1, is the oxidation number of oxygen plus the oxidation number of hydrogen. That the oxidation number of this ion, which is minus 1, is the algebraic sum of the oxidation numbers of all the elements present in this ion. So what this means is that the oxidation number of oxygen plus the oxidation number of hydrogen is minus 1. This is what rule number 3 entails. The oxidation number of oxygen plus that of hydrogen will give me minus 1. Oxidation number of oxygen, of course, is minus 2, plus oxidation number of hydrogen, of course, is plus 1. Will it give us minus 1? Plus 1. Let's check. This is minus 2 plus 1. That's plus 1. Of course, minus 2 plus 1 is minus 1. Yes, this is very true. So this minus 1 on top of the ion, it will just be written as minus. Further on this rule, another polyatomic ion which I can come up with is NH sub 4 plus. You can call this ammonium ion. Ammonium ion. This means that this plus, which means plus 1, is the algebraic sum of the oxidation number of nitrogen plus the oxidation number of hydrogen. This means that the oxidation of nitrogen plus hydrogen is 4 atoms, so I will say 4 into the oxidation number of hydrogen. Will it give me plus 1? Let's check. Oxidation number of nitrogen is plus 5. Oxidation number of, so plus 4 into, no, that won't be. Nitrogen is in group 5 in the periodic table. Nitrogen is in group 5 in the periodic table. That means that it is either nitrogen loses 5 electrons. If nitrogen loses 5 electrons, that means the oxidation number of nitrogen will be plus 5. Or another possibility, because it's in group 5, is either nitrogen gains electrons. How many electrons will nitrogen gain if it's gaining electrons? It has 5 electrons already in the atom shell, that's why it's equal 5. Alright? If it's gaining electrons, it has to gain 3 to add 3 to become 8. Octet structure, octet configuration, that's the aim. Alright? So if nitrogen is gaining 3, of course it's easier for nitrogen to gain 3 than to lose 5. That doesn't mean that there is no case where the oxidation of nitrogen is plus 5. But in this case, it is going to be minus 3, because this atom would gain 3 electrons. Remember, atoms will gain electrons to become negatively charged or to have negative oxidation number. Plus 4 into oxidation of hydrogen is 1. Of course, hydrogen is equal 1 in the periodic table. Alright? That means it would lose 1 electron. It's easier for hydrogen to lose 1 electron than for it to gain 7. If you gain 7 plus this 1, that would be 8. Octet configuration. It's easier for it to lose 1. So the oxidation number will be plus 1. So if you do this, this is minus 3 plus 4. That gives me plus 1. That is why the charge of this ion is plus. So ammonium ion has a charge of positive 1. We can look at other polyatomic ions. Example SO42 minus. SO42 minus. Before you watch this, I would like you to pause the video and try this for yourself. Yes, if this is true. Let's continue. I believe you tried that. And that's true also. Okay, from there, it means that the oxidation number of sulfur plus oxidation number of oxygen. Oxygen is 4 atoms, so 4 into O. Alright, if I add it, it should give me minus 2. So let's check it out. Oxidation number of sulfur, assuming I didn't know the oxidation number of sulfur. Assuming I didn't know that. But I know that of oxygen, which is minus 2. I think we did that here already. Oxygen is in group 6. It's either it loses 6 electrons to have an oxidation number of plus 6, or it gains 2 electrons to have an oxidation number of minus 2. But it's easier for oxygen to gain 2 electrons rather, to have an oxidation number of minus 2. So that's why oxidation number of oxygen is minus 2. So oxidation number of oxygen is minus 2, always minus 2 rather, except in peroxides where it is minus 1. We will come to that much later. But let's find out of sulfur. I don't know the oxidation number of sulfur. So we're still in rule number 3. So oxidation number of sulfur plus 4 into oxidation number of oxygen, which is minus 2, will give me minus 2. So that of sulfur plus minus 8, that gives me minus 2. That of sulfur minus 8, plus minus is minus, that gives me minus 2 plus 8. Sulfur equals to minus 2. I'll take 8 over now, so that becomes minus 2 plus 8. So I can see minus 2 plus 8 is 6. Please always remember to put the sign. Yes, remember to put the sign. So that is plus 6. The oxidation number of sulfur here is plus 6. That is why in this ion is called tetraoxo sulfate 6 ion. Tetraoxosulfate 6 ion. This is the name because sulfate 6, the oxidation number of sulfur is plus 6. We can also have NO3 minus. We are still in rule number 3. So the this is a polyatomic ion, consists of more than one element. The algebraic sum of the oxidation numbers in this atom will give me -1. We know the oxidation number of oxygen, it's always -2, except in peroxides where it is -1. So the oxidation number of oxygen, nitrogen plus 3 into oxidation number of oxygen will give me -1. Alright, let us find out what will be the oxidation number of nitrogen. In ammonium ion, I think I went ahead of myself and I told you the oxidation number of nitrogen, which was -3. So for me to add this and it will give me -1, what will the oxidation number of nitrogen be? So that of nitrogen plus 3 into that of oxygen, which is -2. Of course, this is not a peroxide, so the oxidation number of oxygen remains -2. This is equals to -1. So this plus 3 times -2 will give me -6 equals to -1. So this is -1 plus 6. -6 crosses over. So you can see that -1 plus 6 is plus 5. So you can see there that the oxidation number of nitrogen in this particular atom is plus 5. The other one we had -3. Yes. So this means that this ion is called trioxonitrate 5 ion. Trioxo because there are 3 atoms of oxygen, nitrate 5 because the oxidation number of nitrogen here is plus 5. This is the IUPAC name of this compound, this ion, this polyatomic ion. Let's proceed. If you look at that ion, it's PO43 minus. It means that the oxidation number of phosphorus plus that of oxygen multiplied by 4 will give me -3. So doing this, I will have P plus 4 into O gives me -3. I know the oxidation number of oxygen. How am I going to find the oxidation number of phosphorus? This will be P plus 4 into -2 equals to -3. P plus -8 -3. This is P minus 8 equals to -3. So P minus 3 plus 8 crosses over. Alright, and I have P equals to plus 5. That means that the oxidation number of phosphorus here is plus 5. So that when I add it to that of oxygen multiplied by 4, it will give me 3 minus, that's -3. So the algebraic sum of the oxidation number is equal to the charge of this ion. This is why this ion is called, can you get the name of this ion? You can just pause and get the name. Alright, 4 atoms of oxygen, so I'll call this tetraoxophosphate 5 ion. Tetraoxo because of 4 atoms of oxygen. One atom is mono, 2 atoms is di, 3 atoms is tri, 4 atoms is tetraoxo. Monooxo, dioxo, trioxo, tetraoxo. Phosphate 5. The 5 here is the oxidation number of phosphorus, which is plus 5. Let's look at another polyatomic ion. Another polyatomic ion, we can look at MnO4 minus. If you look at the trend, you will discover that knowing the oxidation number of especially of the elements helps you to predict the name. Alright? Like this one will be, the name of this compound will be tetraoxo, because of this manganese, tetraoxo manganate something ion. So what will be the value here? That value is the oxidation number of manganese. So to know the name of this ion, let's find the oxidation number of manganese. Manganese plus 4 into oxygen equals to the charge, which is -1. Okay, that is manganese plus 4 into -2 equals to -1. Manganese plus -8 equals to -1. Manganese -8 equals to -1. Manganese equals to -1 plus 8. This is equals to -1 plus 8 is plus 7. So the oxidation number of manganese is plus 7. But when I'm going to represent it in the name, I will not put 7 here. I won't put 7 there. I won't put 7 there. What I'm going to use is, I will use Roman numerals. Manganese 7 is written as this. So this is the isopath name of this ion. I still have one interesting ion to show to you. That is Kr2O7 2 minus. Yes, I love this ion. Very interesting. I love this ion. All right. Can you predict the name of this ion? You can pause the video and check that. And a hint, this is 7 atoms of oxygen. 4 is tetraoxo. 5 is pentaoxo. 6 will be hexaoxo. 7 will be heptaoxo. So the name of this is heptaoxo chromate. This is chromium. But I am seeing 2 atoms of chromium, so I will have heptaoxo dichromate. Dichromate, 2 atoms of chromium. I will now put the oxidation number of chromium inside there. Let us find the oxidation number of chromium. So I would have 2Cr plus 7O equals to -2. 2Cr plus 7 into -2 equals to -2. 2Cr plus 7 times -2, that is -14 equals to -2. 2Cr equals to -2 plus 14. Alright, so moving forward from there, we are making progress. This gives us plus 12. Divide both sides by 2. So the oxidation number of chromium is plus 6. but we won't write plus 6, we'll write Vi. So the name of this ion is heptaoxo dichromate 6 ion. This is rule number 3. Let's move forward to rule number 4. Rule number 4 says that the algebraic sum of the oxidation numbers of the elements present in a compound is 0. In rule number 4, we are seeing that there is a difference between a compound and an ion. An ion can be monoatomic or polyatomic. But a compound is different. Ions will have charge, either positive charge or negative charge, but a compound does not have any charge. Or you can say that the charge of a compound is 0. So, the algebraic sum of the elements present in a compound, the algebraic sum of the oxidation numbers of the elements in a compound is 0. Or you can say that the oxidation number of a compound is equals to the algebraic sum of the elements present in that compound. And the algebraic sum of a compound is 0. The algebraic sum of the elements, oxidation number of the elements present in the compound is 0. So I'm not saying the same thing in different ways. Alright. So we can pick any compound. For instance, let's say a compound like magnesium chloride. This is not an ion because I am not seeing positive charge here, I am not seeing negative charge here. This is a compound. So the oxidation number of this compound can be written as MgCl2 0. Just the same way we would like to write an ion putting a charge. A compound like Na2, yes, this means that the algebraic sum of the oxidation numbers of this compound, of the elements in this compound is 0. But the 0 is often omitted. Just the same way for a free state element, a ground state element, that the charge is 0, the oxidation number is 0, that 0 is often omitted. So this is usually written as Na2O. No charge will be written there. Yes. This rule is very interesting, in as much as other rules are interesting. It's very interesting because in this rule, you can find the oxidation number of any of the elements in a particular compound that was not known, as long as the oxidation number of all the other elements are known. For example, look at this compound now. Look at this compound. NgCl2, that's magnesium chloride. What will be the oxidation number of magnesium? Or the oxidation number of chlorine? Let's say the question was magnesium. Because this is a compound, so you can say that the oxidation number of magnesium plus 2 into the oxidation number of chlorine will give me 0. If you were asked to find the oxidation number of magnesium, which is what you don't know, chlorine is in group 7. That means chlorine can either lose 7 electrons or gain just 1 electron as an halogen. So, but the most possible oxidation state of chlorine is -1. So I'm going to use -1 here. There are compounds that the oxidation number of chlorine will not be -1, but in most cases we have -1. So I'll say that of magnesium plus, and this is an ionic compound. Alright? So a metal and a non-metal. Of course, this chlorine is going to gain, and it can only gain 1 to have an oxidation number of -1. So this is plus 2 times minus 1 is minus 2 equal to 0. So oxidation number of magnesium is 0 plus 2. That means oxidation number of magnesium is plus 2. This means that magnesium as a group 2 element would lose 2 electrons. So you should know when the algebraic sum is equal to 0 for a compound and when the algebraic sum is equal to the charge for a polyatomic ion. I would like you to find the oxidation number of sodium in this element, in this compound. If you do that, the oxidation number of sodium, alright, would be plus 1. I've taught you the rules, just use the rule and apply and solve for sodium oxide. The oxidation of sodium will be plus 1. You can confirm that using that rule. Let's proceed. There are 3 points I would like us to note as still part of the rules anyways. The first point is that in a compound, point number 1, in a compound, the more electronegative elements have negative oxidation number. In a compound, the more electronegative elements have negative oxidation number. And the more electropositive elements has a positive oxidation number. For example, this element has a positive oxidation number plus 2 because it is more electropositive than chlorine. And chlorine has oxidation number minus 1 because it is more electronegative than magnesium. In this first point of note, this is not only for ionic compounds. This compound is an ionic compound because this atom is losing electron to this atom, and this atom, chlorine atom, is gaining electron from this atom. So this is not just for ionic compounds. This also applies for covalent compounds. This is very important because for a covalent compound, there is no laws, there is no apparent law of gain of electrons. What happens is that there is a sharing of electrons within the atoms of a covalent compound. So, an example of a covalent compound is H2O. Practically speaking, hydrogen is not transferring electron to oxygen, and oxygen is not gaining electron from hydrogen. Practically speaking, the hydrogen atoms, the 2 hydrogen atoms, is sharing the electrons with the valence electrons in the oxygen atom. But if you want to represent this ionically, this is what you're going to have. Practically speaking, alright, what this means is that hydrogen is losing electron and oxygen is gaining electrons. So even though this is a covalent compound, the more electronegative element would have a negative oxidation number and the more electropositive element will have a positive oxidation number. This is what I mean. What I mean is that apply the rule. This is the same thing as H2O, alright, 0. This means that the oxidation number of hydrogen plus that of oxygen will give me 0. Looking for the oxidation number of hydrogen. That is, okay, let's say that's what I was looking for. Plus that of oxygen is always minus 2, giving me 0. So this is 2H minus 2 is equal to 0. 2H is equal to 0 minus plus 2. 2H is equal to plus 2. Divide both sides by 2. So H is equal to 1 or plus 1. The oxidation number of hydrogen is plus 1. It is looking as if hydrogen is losing electron. But this is a covalent compound. Hydrogen is not losing electron. there is a sharing of electrons between hydrogen and oxygen. But the reason is because oxygen is more electropositive, electronegative rather. So if you have a negative oxidation number, and hydrogen is more electropositive, that's why having a positive oxidation number. So take note, for ionic compounds and also for covalent compounds. The second point to note. In the second point, which is still part of the rules, the oxidation number of oxygen is always -2, except in peroxides. Except in peroxides, where it is -1. Oxidation number of oxygen is always -2, except in peroxides, which is -1. Peroxides are higher oxides. That means in higher oxides or peroxides, the oxidation number of oxygen is -1 is higher than -2. So that's another thing to note. So, example, we have sodium peroxide, Na2O2. This is a peroxide. Here, the oxidation number of oxygen will be -1. Yes, with -1. We still have other examples of peroxides that we can look at. Calcium peroxide. Calcium peroxide. The oxidation number of oxygen here is -1. Alright. We also have barium peroxide. Barium peroxide. That's how it's written. Oxidation number of oxygen here is -1. So, but most other compounds that are not peroxides, that higher oxides, oxidation number is +2 rather. And the third, which is the last point to note, okay, before we look at the third point, there is another peroxide which I would like to introduce to you. That peroxide is Li. Okay, this will be the third group rather. I think we're done with peroxides. Yes. The third thing to note. Let's look at the third. It's in the third. Right. You check up for the other. So, in the third point to note, the oxidation number of hydrogen is always +1, except in hydride, where it is -1. In most compounds, oxidation number of hydrogen is +1, except in hydrides, where it is -1. What are hydrides? Hydrides are compounds formed when hydrogen combines with another element. It could be hydrogen combining with a metal, example, sodium hydride, alright? Here, the oxidation number of hydrogen is -1. How do I know? Because this plus this should give me 0. And for that to happen, that of sodium has to be +1, and that of hydrogen has to be -1, so that when I add, it will be +1 -1, that gives me 0. There are other examples of hydrides, but I love this hydride so much, alright? This is called lithium tetrahydroaluminate 3. Lithium tetrahydroaluminate 3. Lithium tetrahydroaluminate 3. The oxidation number of hydrogen here is -1 because it's an hydride. So you may be, what is the oxidation number of lithium? What's the oxidation number of aluminium? And what's the oxidation number of hydrogen. Of course, we know that of hydrogen. We know that of aluminum. Aluminum is in group 3, so it will lose 3 electrons. So the oxidation number is plus 3. What will be the oxidation number of lithium? Plus that of aluminum plus 4 that of hydrogen will give us 0. So lithium plus aluminum is plus 3 plus 4 into minus 1 will give me 0. That of lithium plus 3 minus 4 would give me 0. So that of lithium plus 3 minus 4 is minus 1, gives me 0. That of lithium will give me 0 plus 1. That of lithium would give me plus 1. So the oxidation number of lithium here is plus 1. The oxidation number of lithium in lithium tetrahydroaluminate 3 is plus 1. Why are we calling aluminate 3? Aluminate 3, that is how I knew that the oxidation number of aluminum here is plus 3. Lithium is obviously in group 1. One's valence electron, it will lose that one valence electron. So these are 3 points to note as far as oxidation numbers is concerned. Just watch for the next video on calculations involving oxidation numbers. Meanwhile, we've done calculations involving oxidation numbers. If you still want more examples, there is a video in the comment section that will look at a few more examples on calculations involving oxidation numbers. Thank you so much for watching this video. Make sure you like, make sure you subscribe, make sure you share. Thank you. See you in my next class.